All right. Hello, everyone, and we're live here at the Construction Engineering Research Lab, which is a part of ERDC, and we are here with Megan Kreiger, who happens to be the program manager for Additive Construction, and today we're talking about ACES JCTD. So, Megan, tell me, what is ACES JCTD?
So the ACES JCTD is the Automated Construction of Expeditionary Structures Joint Capability Technology Demonstration. This is where we're using additive construction technology, which is essentially anything 3D printing related to construction, so using things like concrete or foams that you can use in construction, where we can use this in more of an expeditionary type setting with a very mobile 3D printer, using local materials on demand, on site, with custom designed structures in the field.
Okay, that's amazing. So, so in this particular project, you guys are planning on doing a gap crossing, right? A bridge.
That's correct. Right now, we are working on constructing a 40-foot gap crossing to support vehicle loads that we currently have Marines and Seabees out there working with our ERDC personnel to learn how to 3D print and basically emplace this gap crossing.
Okay, so when I imagine 3D printing, right, I imagine a little box, right, that we put plastic through, heat it up, and then it can make awesome forms, right? How close to that is what you're talking about?
So regular 3D printing versus additive construction. With regular 3D printing, typically you're printing small parts, trinkets, other things like that. For additive construction, we're talking about printing full-size structures or components for buildings. So when it comes down to it, the really big difference is your materials. So instead of feeding, say, a roll of plastic filament that has a high amount of quality control before it even comes in, we're printing with concrete. And concrete comes with a number of different challenges, including the aggregate size, the flow, and here we're actually stepping it up in our challenging where we are using locally available materials. So we don't get pre-bag mixes and go into a site. We're talking about taking our sand, our gravel, mixing it all together based off of those locally available materials. That means we, instead of producing a small part, since we're going for more of construction, you can fail on a small part and just reprint it. When you're printing a building, you want to make sure it's right that first time. So you have it as a actively controlled 3D printer, and it's still construction is the big part, right? Is like, we aren't talking about you push a button and it just lets the 3D printer go, you can walk off, come back, and there's a part. We're talking about construction, just reducing that manpower and hard labor associated with it.
Okay, so how is this different, forgive me, right? But how is this different from just like making a bunch of wooden forms, right? And then just pouring concrete into wooden forms? Why is this better?
So the first part about using formwork for construction is you have to have the forms on site. That means you either need to pre-build them and ship them to wherever your location is, or you have to have the supplies. And in the US, we typically think about wood as something that's easy to come by, easy to work with. But around the world, a lot of places don't have pine timber, and so we're working with hardwoods. And when you have to construct forms out of hardwood, that's a whole nother ballgame. But also when it comes to formwork, they are extremely labor intensive to build and maintain, which means both you have the logistics of getting them out to the field as well as maintaining them. With 3D printing, there's no formwork required. So you can just start printing whatever shape you want, and they're fully customized, right? So like, if you expect to build something in the field and you realize it doesn't quite meet your needs, you can customize that design on the fly with 3D printing to really meet the mission at hand.
Okay, and so just as a baseline, right? How long would it take to 3D print a building? Like a one-story building that would have like 2 rooms in it?
Yeah, so we've demonstrated that you can print a 500 square foot building, the walls of it, in approximately 48 hours.
Oh, wow.
And so that's of actual time. In the field, there is this difference between print time and actual time. A lot of people report print time, which is just the time that the printer is running, which that building took us about 14 hours of print time, but it was split over about 48 hours.
That's amazing. So that's probably a bit faster than what we're doing right now, right? How we're building expeditionary structures?
Correct. So typical structures, depending on the type, whether it's a wood structure or a CMU block, take around 3 to 7 days in order to construct those buildings. And so if we're able to reduce that time down to 48 hours, that means we're a much more mobile force than we would have been.
Okay. So the end goal really, right, is to bring less of prefabricated structures and prefabricated materials to the location, right? And instead use raw materials.
Exactly. And so instead of us bringing a lot of materials with us, when you think about construction, you typically think of the equipment, right? But the equipment is just using those raw materials, and the massive amounts of shipments are typically those consumable materials that you're using. If we can reduce the amount of transportation time and location, then we can get things built faster. And so what that means is we can build a large amount of things with just materials that we can find relatively locally.
Okay. And what has led us to this moment right now? So how did we get, 3D printers had to be invented, sure. But skipping that, how did we get to this moment right now, attempting to 3D print a gap crossing?
Absolutely. So in 2015, we started the original Automated Construction of Expeditionary Structures program, where we built a 500 square foot building with just our personnel. And in that, we developed the printers, the mixtures, the methodologies in order to be able to print these types of structures. From there, we took those designs and we started working under a cooperative research and development agreement with Caterpillar, as well as a number of other partners on different projects, in order to develop this technology to be more ruggedized, more transportable, to use those locally available materials, as well as starting to automate that concrete mixing process. And so right now, underneath this project, we're really working on being able to develop local mixtures, be able to increase our quality control, as well as automation. On top of that, exploring the blast and ballistics of these types of structures, and then getting into what we're into now, which is more of the expedient gap crossings. And so as we continue to develop, we've been through multiple iterations of printers and methodologies in order to get where we are at today.
Okay, and then, so it's important in an expeditionary setting, right, for these 3D printers, but where else could we see these 3D printers being utilized? Like, could we use them in humanitarian or natural disaster relief? Absolutely.
So the advantage that 3D printers provide in humanitarian aid, disaster relief, is that you're able to apply this technology towards that specific need for the site. So whether you're talking about fires or floods, you now have the option of using the same equipment, just changing the design that you put into that printer in order to build things like jersey barriers, different types of structures, different types of gap crossings, things that are necessary for that site just to be able to get supplies in and out and get people in more of a protected environment.
Okay. And we're going to open up the floor to questions soon, right? But is there anything else you want to add to this process? Like, how has this process gone for you?
Absolutely. So this project has been a partnership between U.S. Southcom, U.S. Indo-PACOM, Navy, Marine Corps, Air Force, and we've been really working hard in order to be able to establish this as more of an expedient technology. We've also been working inside ERDC with the GSL down Vicksburg in order to be able to get these kinds of structures tested. And so underneath this, this is just one of the demonstrations that we're currently working on, where we're going to test this in more of an operational environment when it comes to next year. And so I just really want to emphasize the amount of work that the team has done, both at ERDC as well as the external partners, in order to be able to accomplish these goals.
Okay. And so Cyril obviously does work with this, right? This is construction, right? Mm-hmm. But what other work does Cyril do?
So Cyril does a wide variety of different research areas, everything from endangered species to doing paint testing, as well as even robotic construction equipment, so having like remote controlled excavators or autonomous excavators. all the way to additive construction, so 3D printing with concrete, foams, other materials. So it's basically anything that would apply to essentially improving military environments.
Okay, and then when I think of 3D printing a bridge, right, in my head, right, I imagine we put a structure, a crane, right, a printer over the gap, and then it would just go forth, right, and print a bridge. I imagine it's a bit more complicated than that.
Yeah, yes, exactly. So underneath this project for this gap crossing, we really have a number of different constraints that we're operating underneath. So typically people think of construction of bridges with lots of heavy equipment, they got cranes on site. We're limiting this to just like an 8,000-pound forklift in order to be able to move all these pieces and parts in place. So that means we're building this gap crossing in a lot of different components. Then we're going to be post-tensioning, using post-tensioning bars to get this entire thing built and across the gap, using technology similar to what Expedient Bridges already use, which is the rollers to place things like Lock B and other types of military bridges.
Okay, so forgive me, all right? I'm a bit of a layman, right? So when I'm about to post on social media, I feel post-tension, right? But tell me about post-tension as it applies to bridges.
So what we do is we are printing essentially leave-in-place formwork for this gap crossing. They're called box beams, and they look kind of like bent horseshoes. And inside that horseshoe type shape, we're putting in basically conduit, they're called ducts, and we are also putting in reinforcement. So that means rebar as well as ladder wire. In that, after all of that is cast inside of that area, we are going to be rotating these 90 degrees and putting in post-tensioning bars. That's a bar that goes through that we're able to tighten down with nuts in order to make the entire bridge one piece. Each of these is assembled and rolled out over the gap with a counterweight on the back in order to get this gap crossing across the gap. This one in particular is using multiple strands, so we're printing smaller components in order to be able to meet that forklift requirement and putting each of these strands over the gap to make one complete bridge.
How cool is that though, really? Like to essentially build a bunch of Lego blocks, right, that will eventually just become a bridge. Can we just take a moment and sit in that? So like, how did all of that come to be, right? Were you the person who was like, hey, concrete 3D printing's a thing, let's make a bridge out of it? Who thought of this wonderful idea?
So this was actually a requirement put on us for this specific project in order to be able to do bridges. We mentioned it as one of the potential applications. And here we're really pushing the bounds of what is possible for this technology. Right now. And so with this, people might say something like, well, why are you printing the same shape over and over again? We have to remember this is the military, right? So if we're talking about constructing a bridge, we don't want some crazy optimized structure that when the military personnel look at it, they go, how am I supposed to put this together? They want something very straightforward that we can assemble fairly simply and be able to cross that gap. And so here, when we're successful, this will be potentially the first vehicle 3D printed bridge in the world.
Wow, that's amazing. And we're gonna just eventually, right? I know that you guys have a bit of work to do as far as like measuring stress points, right? And things like that, structural integrity before you guys do that. But you have high hopes that we'll see a vehicle going across it?
We hope in the future that we'll be able to get a vehicle across the bridge. This has been structurally designed, and we're running through structural testing to see what types of loads it can support. And after we've verified that it meets those loads, then we'll be able to do more testing.
Okay, that's amazing. Well, we're going to go to the audience and see if they have any questions for us. So we've done bridges, we've done houses. What is next?
So we're actually we're working with multiple groups to develop building codes. So across the spectrum, trying to take things all the way from down at the materials testing all the way up through establishing the building codes. That's really where a lot of our emphasis is right now, as well as exploring printing more operational type structures. So buildings, more things like barriers, jersey barriers, and being able to test these and see how they operate in the environment. So with this, there is a lot that is being currently pushed in the field towards printing buildings within the government as well as outside the government. And we're really pushing towards a standardized testing requirement, making sure that these structures are safe for occupancy, as well as, running through and understanding the performance of things like gap crossings and jersey barriers as well. It's kind of an entire spectrum of things that we're working on right now. We also work with a number of private sector partners. So testing those printers, seeing what the changes that need to be made in order to make those more reliable pieces of equipment before they are sent out into the field for further demonstrations. This also allows us to get a wider perspective on the field and which technologies are more applicable to the military, and to be able to run through and troubleshoot those issues for the government.
Okay, so I know that there are various methodologies when it comes to 3D printing, right? Like even plastic 3D printing, right? There are people that allow for multiple different materials to go through the extruders, right? There's different build platforms, right? There's even the amount of articulation in the X, Y, and Z axis for the extruder, right? So that same thing probably applies to concrete 3D printing, right? I imagine out there is a 3D printer with all the bells and whistles that you could ever imagine, right? But that's not probably going to be as effective in an expeditionary environment, right?
Right, so there's a wide variety of technologies. So there's everything from using robotic arm type 3D printers all the way through to typical gantry like what we use, and everything in between. So ones that are cantilevered, it's the whole spectrum. And a lot of those printers rely on a highly consistent quality material, which is just really difficult to find in the field. I mean, a lot of times the warfighters are working on problems like, can we use pre-cured cement, to reuse it for construction? And so when you throw 3D printing into that equation where we have concrete hoses or material hoses feeding cement, then you start having those like, well, you can't have those massive chunks in there of hardened cement. And it's just kind of it's a compounding problem, right? And so when it comes down to it for use in the field, we're really looking for being able to use those raw ingredients. And there's a wide variety that we've looked at, including using like elastomers with different partners to mix with sands and other aggregates in order to make a different type of material. We're also looking at what are the alternatives to the traditional Portland cement that make this a more green type environment for printing. But the field has everything from using, UV cured materials all the way through to using polymers. And each of those kind of has their place. And when they're based off of a very mobile printer that is more simplistic, that can use those local materials, then you're talking more of an expeditionary setting. One of the things that I've seen is that a lot of times engineers want to solve the problem for the personnel, right? Is that if you add a lot of sensors, you make the machine a lot more complicated, then the personnel only have to deal with a limited number of problems. But when you put them in more of an expeditionary type setting, if something breaks in the field, if you have a lot of sensors, a lot of those things on there, you have a lot of fail points. And so as long as those sensors are not immediate fail points and you can override them, then you're talking more of an expeditionary type printer. But throughout this process, we've really been developing the entire system for military personnel. So kind of the complete opposite look at what typically happens where someone develops something in the private sector and the government buys it. We're talking about, let's start from the get-go of how do we develop this for military. So everything's ruggedized, you could probably drop parts of that printer out of a truck and pick them up and still use them as part of the printer. And that's really what we're talking about is how do we make a printer that can take a beating and still keep going? Because that's what the field is going to need if this technology is going to transition.
Okay. And, not to bring it to space, right? But when we send stuff into space, we only have so much room, right? And we can only carry so much. An expeditionary environment is a lot like that, right? You can only hold so much and carry so much with you. So the ability to use raw materials that may not be best case scenario, right, in terms of raw materials, but good enough to get the job done materials, that's your goal here?
Yeah, and so exactly, because a lot of these structures have a limited lifetime. So we're talking about, if we need a building that only has a 5-year lifetime, what type of material properties do you need to support that, as opposed to a structure that will last 100? So you might be looking for different things when we talk to, within the continental United States versus if we're going to a more expeditionary setting. Also, with that, when it comes to space, there is a lot happening for the development of this technology area for space. We previously worked with NASA, Kennedy Space Center, and Marshall Space Flight Center on some of the technology in this area, and they've continued to work on that area of using regolith, both lunar and Martian, in order to be able to print on the moon and Mars. So you can learn more about that by visiting the NASA website.
Okay. What are the challenges? Because looking at the footage that we shot throughout this week, you all make it look pretty easy. So what are the challenges when you're 3D printing with concrete, which is, as I understand it, like warm mud, but a little thicker, right? Because I see a lot of the guys, they reach in to test, right, how the viscosity, right, of the concrete. Tell me about that.
Yeah, so the major challenge with concrete 3D printing is the concrete. While it's a material that has been around for ages, we're looking for different properties than people typically look for. So, it needs to be able to flow through a concrete hose without clogging it up, but it also needs to be able to support and have the compressive strength as a uncured material that's strong enough to support successive layers on top of it. And so when it comes down to it, the materials are the difficult part. And we make this even harder for ourselves by using large aggregate as well as using raw materials. So we've previously shown you can use a pre-bag mix in a fairly simplistic mixer pump and operate our normal gantry system with one of these mixer pumps with just 2 people, right? What we're talking about here, though, is we want to be able to use raw ingredients, so not those pre-bag mixes. With the raw materials, it takes a few more people in order to be able to get the job done. And so we're using any mixers that are available in the field. So during this demonstration, we're using a volumetric mixer that's available for the military currently in their inventory. Yeah. But we're not limited to that. So we could use a drum mixer or a pan mixer. Our system is capable of integrating with any of those types of mixing systems.
Okay. Because it's easier, right? It's easier logistically.
Exactly.
Right? To not have to bring everything with you.
Exactly.
That means less flights, right? Or less trucks, or less any planes, trains, and automobiles. Let's talk real here for a second, Megan, right? It means less transportation to get our people to where they need to go.
Exactly. And on top of that, too, it's why make somebody buy an entirely new mixer when you already have a bunch of mixers in the government? Some areas you might have a drum mixer and people that are proficient with that, and you might be feeding buckets to it, and that might be the best way for that printer in that environment to operate. Whereas other places, having one of these volumetric mixers, it improves the quality of the concrete because it's more automated. Basically what it does is it measures out each individual material and makes sure it's consistently the same material as you keep mixing. But there are environments where you don't have that, and so you need that flexibility in order to operate that way. It just wouldn't make too much sense in order to make the military buy another mixer when we already have a number of them within the government.
Okay. And all of it, the 3D printer that you guys currently have, like fits in a box, like a Connex.
Correct.
Right? There's a fancy name for that, right? Like ISO something something number.
Yeah, so this gantry system, aside from the mixer, which is whatever you have available on the site, the entire system fits within a 20-foot shipping container. So, and that whole container is less than 10,000 pounds. And so we're talking about being able to ship, a printer, get the locally available materials for less transportation, less logistics than it would take to get jersey barriers to the field.
So like 2 pickup trucks.
Exactly.
Ish.
Exactly.
Really. Not to quantify it, but about 2 pickup trucks. We do have a question from the audience, if you want to hear it. Our good friend Matt Fry is asking, what's next for the team?
So the team is currently working on establishing the appropriate testing methods for being used for building construction. So that means being able to develop what types of material tests you need for verifying that your structure is structural, right? Is that when it comes to 3D printing, it's different than cast structures. And we need to be able to understand that difference in order to be able to quantify it and be able to do those structural calculations in order to make this acceptable around the United States and the rest of the world.
So, sorry, but a cast structure, is that like when you see a concrete I-beam? Like that's a cast structure?
Exactly. So typical testing that's done for concrete is you take something like a cylinder and you fill it with concrete and then you crush that cylinder. The thing is, when you're doing that, you're assuming that your concrete is just one fill material, right? But with 3D printing, you're in layers. And so there is a difference between how those layered concrete beads stack up and then perform under something like a compression test versus filling a cylinder and crushing that. And so we're working on everything from developing those materials tests with industry and all the way up through developing that structural code of what do people need to look for in these structures to make them occupiable. That's just one piece of what we're working on. We're also working with multiple different partners on developing different materials to be able to use for 3D printing. So that means things like elastomers and alternative materials, as well as going into doing a more operational type structure in the field sometime next year.
Okay. Are you excited for that?
Absolutely, yeah. When we do buildings, they're actually much more simple than bridges. So bridges have to actually support a load going over top. Buildings are stationary. Their reinforcement is much more simplistic with how they're done. Bridges are much more complicated when it comes to how do you support these loads. They resemble more along the tunes of a roof, which is one of the reasons why we're interested in bridges, because if we understand how bridges performs, we also understand slightly how roof structures perform.
Because they have supports, right, that support the roof on 4 sides, while a bridge is more just support from underneath across the entire
Exactly,
But
exactly.
I imagine there's a lot that translates between those two.
Exactly, and so when we're talking about putting bridges in place, it's not just the printing. The printing is actually the easiest part of this process. It's actually, for us researchers, the hard part is the actual construction process. So how do we get this in place? How do we assemble this? It's the 3D printing compared to the actual full construction process is the easiest part of the problem.
Okay, well, I don't think we have any other questions, and we're almost out of time. But thank you so much for sitting down with me today. I know it's been a crazy month, year for this project to come to fruition. So thank you for taking a little bit of time out of your day to speak with us about additive construction.
Absolutely. Thank you for asking me here, and we'll keep everybody updated as we proceed along on this demonstration.
Okay, thank you so much. Well, thank you guys for joining us today. We are hopefully going to be posting some pictures as we go along during this process. We're about halfway through the process right now, but stay tuned in these coming weeks to see more pictures of this project as it pushes forth. So, once again, Megan Kriger, thank you so much.
Yep, thank you.